Swayam Prabha. Digital India. Educated India.
So that's what is carried even here in this third point is the finite temperature difference. So you can see that the temperature difference is a force here, which is going to lead to heat transfer. Yeah, so these are all, I mean, we have already discussed this. So yeah, so this example will see how to make the heat transfer reversible. That will come in the next slide. Now let us move ahead and say that what is the other thing, fourth important factor that leads to irreversible things. The fourth turns out to be mixing of substances. So mixing of substances is inherently irreversible. Now to see that, again, you can go back to the example of expansion of a gas. So here you can, so there we have one gas which is going into vacuum or at something at a lower pressure. Here you can think of there are two species, species A and species B, and they're diffusing. They are moving from one region to the other region, just like a perfume bottle opened at one end of the room, we smell the perfume at the other end of the room. Okay, so essentially you have perfume molecules uh, diffusing into your air molecule and so on. So you can again think of that it is an unrestrained expansion of the species A into species B and vice versa. Okay, so that is very similar. So very similar arguments or the same argument is even there as well. So once you understand, so the key is to understand this example again, the expansion of the gas in a vessel. Okay, once you understand this example, everything else you can see. And the bottom line here is that a finite force gradient leads to irreversibility. And to make it reversible, you need an infinitesimal force gradient. Okay, let me pause here and see any questions here. Of course, you can understand friction very easily. And of course, the other 3 points are essentially the same. Okay, unrestrained expansion, heat transfer, and mixing of substances. And of course, fifth is the other factors, which could be hysteresis, it could be combustion, and so on. Hysteresis is, again, it's very similar to not having the same path, those who have not been exposed to hysteresis earlier. And hysteresis typically happens because of the non-linearity in the system. Okay, this non-linearity we have not been exposed to at this stage, so I will not talk about too much about hysteresis. But hysteresis essentially arises because of non-linearity in the system. Of course, there could be other reasons, but primarily it is, or one of the non-linearity typically leads to hysteresis. Let us put it that way. Okay, somebody turned his mic on, so I'm assuming there's a question.
I don't understand why finite difference leads to irreversibility. Finite difference in any quantity like temperature, pressure. So why does it lead to
Yeah, so
irreversibility?
the same thing which is here. So if you understand this and this example, okay, so again, what we are saying here is when you're pushing out, okay, you are doing work against this P1. When you're pushing in, you are essentially doing work against P2. And therefore, the work which is done in the two strokes is different. And of course, that means that there is a heat transfer. So the difference in the work goes as heat, and therefore the surrounding has now been changed. Okay, so that's the reason. And of course, we said that if you were to do it with respect to a sandbag, removing very, very slowly the pebbles which are there, sand pebbles which are there, then of course you can have the process being reversible.
Okay, so I got the first point, but how does this lead to reversibility? Matlab? I got the first example why it
Yeah, so
was
here what you would see is that you are essentially changing
change
very,
in
very small here things here. The pressure and the volume keeps on changing. And you go from one state to the other state. And then when you reverse it, you would go exactly in the same path. Okay, because it's again a very small change that you're making, and again a very small change that you're making, and so on.
Okay, sir. Okay, all
Right.
right.
We will go back the same forward and the reverse paths.
Okay, sir. All right.
Any other question?
Excuse me, sir.
Yeah.
Sir, in the definition of reversible process, you said that the path is going from, say, like one position of P comma V to another position. So are we saying that these 2 points are the equilibrium points of our system?
Yeah, that's actually a very interesting point that you have raised. So basically, we had said when we were talking about equilibrium, quasi-equilibrium idea, we said that if it is a very fast process, then we do not even know how we moved from 1 to 2. We only know the end states, end points. Okay. Here it is very clear that we know the initial point because, so initial, how do we get the end point? We said that if we keep the system long enough, then it will attain equilibrium, right? So if so, initially we can assume that the gas is for a long time, and then we have removed the pin. So our state one is very well defined. Similarly, the piston, once it moves up, it hits the stop, and then it again. So maybe immediately, as we had said earlier, if it's a very violent expansion, then the gas inside has not been able to attain equilibrium. But after a very long time, then of course things will attain equilibrium. Okay, it has the piston is now resting at the stop, and then you can assume that I have given a lot of time for the gas to stay in that state, and therefore it has attained equilibrium. So what I'm saying here is that you know the end points only 1 and 2. You do not know how you went from 1 to 2. Okay, so you do not know any intermittent points in this case, which can happen.
So does it mean that for defining reversible, we are saying that we don't care about these intermediate points? If I'm going from one state to other, I must be able to come back, right?
Yes, and unless and until you can define the state in between, you cannot come back. So we are saying the opposite to what you are thinking. So we are unless and until you know all the states in between, okay, then you are not going to get a reversible process. The reversible process will only happen if you know all the states in between, and of course you can reverse the states altogether in your reverse stroke, reverse path when you take the reverse path.
So, but then doesn't it mean that it is in quasi-equilibrium at each and every point?
So that's why we clarified quasi-equilibrium and reversible. So for the process to be reversible, it has to be necessarily in a quasi-equilibrium state. We have already said that.
Okay, sir. Thank you.
Okay? Because you will see that otherwise what is going to happen is you are always going to change the state of the system or the surrounding. Any other questions? Because this reversibility is one of the central or the key ideas. So I'm pausing here quite a bit and waiting for any questions that you may have. So if you were to sort of condense everything and say what is causing to irreversibility, so we had seen 4 factors, and all of these 4 factors can be divided into 2 broad categories. One is the lack of equilibrium during a process, okay, and which essentially means that it is happening at a finite rate, okay, and the other one is because of the dissipative effect like friction. So if you have equilibrium not being satisfied, then it is definitely irreversible process. And if it is a dissipative process, that means that there's friction or there is like ohmic heating or such losses, like if it is an electrical system that you're looking at, then of course equivalent of friction is I square R loss in an electrical circuit. So all these dissipative effects would lead to irreversibility.
Sir, so a irreversible process can have a quasi-equilibrium condition cold.
Correct. So quasi-equilibrium is going to be required for, say, for example, if you look at friction, okay, so as the things are moving out, things may still be moving very slowly. So you have equilibrium, that's not an issue. Equilibrium is not an issue. So quasi-equilibrium, so typically you would have equilibrium or quasi-equilibrium assumption being satisfied, okay, but still the process may not be reversible, okay, which is the case, for example, with friction. Okay, and as we also said that if the process is, if the gradient is small, then the equilibrium assumption can be satisfied, but reversibility, the process is still not reversible. Now, if the delta T, delta P, delta F is very large, then you would have both quasi-equilibrium and irreversibility or being not there, okay, or yeah, equilibrium and irreversibility or reversibility not being there.
Excuse me, sir.
Yeah.
Can we say that the quasi-equilibrium process is a necessary condition but not sufficient condition for
Correct.
the reversible?
Correct. So that's what you can say. So quasi-equilibrium is like a necessary condition for irreversibility to happen, and otherwise, and but not sufficient. So again, these 2 points here illustrate that very well. The moment you have lack of equilibrium, it is definitely irreversible. Okay, but in the second case, you can still have equilibrium, but still you can still have irreversibility. Okay, because of the dissipative effects. So therefore, this condition itself definitely leads to irreversibility. But this condition, if it is satisfied, does not necessarily mean that the process cannot be irreversible still. Okay, the process can still be irreversible if the second thing is present. Okay, or even if a small gradients are present. I mean, small but not infinitesimal gradients are present. Okay, now as we had said that we will take one example of heat transfer where we can have reversible or irreversible. Now, this is an interesting example of phase change that we have looked at, liquid and vapor both existing. And you're heating up the liquid, and of course, that gets converted into vapor. So here what you would see is there is a very small, so inside you can see that the moment a small amount of heat gets added to my liquid, some amount of vapor or that liquid evaporates and gets into vapor. So you can see that inherently here, there is a dT which is there. It's a very, very small gradient which is driving this conversion of liquid to vapor. So inherently, this is an internally, or this we can say it's an internally reversible process. Okay, so although we are saying that most of the time we will have systems which are irreversible, but here now we have an interesting system which is inherently reversible. Okay, that is reversible between the vapor and the liquid. However, when we look at the heat which is being supplied from outside, okay, the heat can be at a temperature T plus delta T. If it is a T plus delta T, then you can see that the system is externally irreversible. Of course, if you were to make it externally reversible, then you will have to supply heat at T plus dt. Okay, that will also make it externally reversible. Okay, so again, the point here is there are 2 points. One is whether you have a finite gradient or you have an infinitesimal gradient. Second, that the phase change processes are inherently reversible. Okay, so these are the 2 things that we are seeing here. Okay, so thank you all.